picture this. You're 16 years old, sitting in a high school math class.
Oh, yeah. The classic scenario.
Right. The fluorescent lights are buzzing overhead. The chalkboard is covered in this, like, dense, impenetrable forest of algebraic equations.
Just completely overwhelming.
Exactly.
Yeah.
And you are staring blankly at the numbers. You tap your pencil, you look at the clock, and you think that, that universal age-old teenager thought, which is, when am I ever going to use this in real life?
It is, it's the ultimate pedagogical hurdle, honestly.
Yeah, totally.
Because convincing a teenager that three-dimensional Cartesian vectors or, spatial visualization actually matter to them.
Good luck with that.
Right, especially when their immediate reality is mostly concerned with social dynamics and weekend plans. It's incredibly difficult.
And usually the answer provided by the textbook is some fabricated, deeply unconvincing word problem.
Oh, the worst.
You know the ones. Like a train leaving a station at 40 miles per hour, or, I don't know, someone buying 60 watermelons at the grocery store.
Because that happens every day.
Right. It feels totally disconnected.
Yeah.
But today's deep dive is going in a completely different direction.
It really is.
We are exploring a fascinating 2004 academic paper by Elena Thibault-Tadeo, and it details something called Proyecto CUBE, which is a teaching proposal that took a notoriously difficult demographic of students.
Fourth-year Spanish secondary education students, to be exact.
Yeah, exactly. And it managed to trick them into eagerly learning advanced 3D analytical geometry.
And the hook wasn't, a better textbook or a more enthusiastic lecture.
Nope.
The hook was a movie, specifically Vincenzo Natali's 1997 cult sci-fi horror film, Cube.
Which is such a wild choice for a math class. If you haven't seen the movie, the setup is provided right in the paper, and it's a brilliant premise for capturing a teenager's attention.
It really grabs you instantly.
Right. So a group of strangers wakes up with no memory of how they got there, trapped inside this giant lethal structure.
It's essentially a nightmare.
Yeah. And this structure is entirely made up of smaller, identical cubic rooms. Every room is exactly 14 feet on a side.
And there's a hatch on every single wall, right?
Yeah, the walls, the ceiling, the floor, all leading to identical adjoining rooms. Oh, and here is the kicker. Some of those rooms contain incredibly gruesome, deadly traps.
Like acid sprays.
Acid sprays, razor wire, you name it.
So the characters aren't just trying to solve a math problem for a grade. They are trying to survive.
The ultimate motivation.
Exactly. The stakes couldn't possibly be higher. And by bringing this narrative into the classroom, the teacher immediately bypasses the students' natural defenses against learning.
Because they aren't doing math, they're escaping a death trap.
Exactly.
Okay, let's unpack this. Because going from a terrifying sci-fi death trap to a high school geometry lesson requires us to understand the architecture of this nightmare.
Right.
The students, just like the characters in the movie, first have to figure out the sheer scale of their prison.
Because you can't escape a maze if you don't understand the shape and boundaries of that maze.
Makes sense.
And the paper outlines the specific clues the students are given to work this out, which they're drawn straight from the film's dialogue.
Oh, that's cool.
Yeah. For instance, an architect character named Worth reveals that the outer shell of the structure has an area of 1,432 square feet.
Okay. And then you have the math prodigy character, Levin. She takes that piece of trivia and makes a crucial deduction.
Right.
She guesses that there is a gap between this outer shell and the massive rooms inside, and that this gap is exactly the width of one small 14-foot cube.
And using that hypothesis, she calculates that there are exactly 26 cubes along each edge of the giant structure.
So it's 26 rooms wide, 26 rooms deep, and 26 rooms high.
A perfect cube itself.
Right. You multiply that. So 26 times 26 times 26, and you get 17,576 interior cubes.
That is just huge.
It is a massive, macroscopic, homicidal Rubik's Cube. But wait, I have to push back here.
Sure, go ahead.
If it's just a static grid of 26 by 26 by 26, and they know the overall dimensions, why can't they just pick a direction, say up, and walk in a straight line until they hit the outer shell?
Well,
I mean, sure, they have to dodge traps, but geometrically, it's just a straight path to the edge, right?
what's fascinating here is that the cubes are not static. They move.
Well, of course.
Yeah, the physical space is constantly shifting, mechanically sliding around inside that outer shell.
You can't just walk straight.
Exactly. This completely shatters the idea of just walking in a straight line because the room you were in a minute ago might now be on the totally other side of the structure.
Oh, wow.
To understand how they move, The students are introduced to the concept of Cartesian coordinate systems in 3 dimensions.
Okay, because every single room has a plaque inside the door.
Mhm.
And on that plaque is a 9-digit number grouped into 3 sets of 3.
Right. And those numbers are the key to the entire puzzle. They aren't just, serial numbers or random
It
identifiers.
actually means something.
Yes, they are coordinates and movement vectors hiding in plain sight. And decoding them is the core algebraic exercise the students are tasked with.
I want to break down how this works because the paper actually lays out Levin's formula, but without getting bogged down and doing the actual arithmetic on the air.
Right. Let's keep it conceptual.
Let's say you open a hatch, and the room number is 320-176-223. How does a student translate that into a physical location?
The mechanism is wonderfully elegant. You take that 9-digit number and you break it into those 3 blocks of 3.
Okay.
The first block represents your x-axis, the second represents the y-axis, and the third represents the z-axis. To find your starting coordinate in the giant grid, you simply sum the digits of each block.
So if the first block is 320, you just add them together to get 5.
Exactly.
That means you are in position 5 on the x-axis. You do the same for the y and z blocks, and suddenly you have an exact pin on a 3D map.
You know exactly where you are.
But you mentioned vectors. How do we know where the room is going to slide next?
That requires finding the displacement values. So instead of adding the digits, you subtract the consecutive digits within those same blocks.
Wait, how do you mean?
Like the first digit minus the second minus the third, and the third wrapping around to minus the first.
Wait, slow down. If I subtract a larger digit from a smaller one, I'm going to get a negative number.
Right.
What does a negative coordinate mean inside a giant cube? If my displacement for the x-axis comes out to -3, what is the room physically doing?
Imagine you're standing inside the room. Let's map it to physical reality. The x-axis dictates movement left to right.
Okay.
A positive x displacement means the room shifts to the right. A negative x means it shifts to the left.
Got it.
The y-axis is forward and backward, and the z-axis is your vertical movement shifting up or down a floor.
That makes perfect sense. So if you sum the digits, you get where you are.
Yes.
If you subtract the digits, you get the vector of where the room is about to slide. You add those 2 results together, and you know exactly where the room will be after the next mechanical shift. And the students track these movements on paper until the room loops back to its starting point.
Right. It's a closed mathematical system.
But movement is only half the problem, right?
Oh, definitely. Escaping the maze doesn't matter if you walk into an acid trap along the way. The students also have to calculate which rooms are lethal.
Initially, the character Levin thinks that any room with a prime number in its identifier is trapped. So a room like 563, because that's prime, will kill you.
But the rule is actually more complex than just simple primes.
Oh, really?
Yeah, a room is trapped if its number is a power of a single prime number.
This is such a great mathematical twist. Take the number 128.
Right.
That is an even number, not a prime number. But 128 is 2 to the power of 7.
And 2 is a prime number.
Exactly. Therefore, room 128 is rigged to kill you. In the movie, there's an autistic savant character named Kazan who does these massive prime factorization calculations in his head to guide the group safely.
Which forces the high school students in the real world to practice factoring large numbers and identifying primes just to verify if Kazan's mental math is actually correct.
I just have to marvel at this for a second. Finding a fiction movie that treats math with this level of rigor is incredibly rare.
It really is.
The math actually works. It's not just random glowing numbers on a computer screen to look techie. It is a fully functioning mathematical puzzle that a teacher can literally put on a chalkboard for teenagers to solve.
So they figured out the math in a vacuum, but getting a movie character to do this is one thing.
Yeah.
How on earth did this teacher get unmotivated 16-year-olds to actually care enough to do these calculations?
That is the million-dollar question. How do you execute this in a real classroom?
Yeah.
And the paper relies heavily on the psychological theories of Feuerstein,
Oh, interesting.
specifically his concept of the mediated learning experience.
Right. Feuerstein's method is about the teacher acting as a mediator between the student and the world. The goal isn't to transmit information, but to alter the student's cognitive structure so they can process information themselves.
Make them think differently.
Exactly. And the paper highlights several of his specific categories applied to this project. The first is intencionalidad, or intentionality.
What does that look like in practice?
Well, the goal isn't to force the student to memorize a formula. It's to actively implicate them in the learning process. The teacher's intention is to make the student want to engage.
That leads directly into a second category, significado, or meaning. You have to make the learning meaningful to their own system of values.
Right.
If you tell a teenager to find the vector of a train moving toward Chicago, they fundamentally do not care.
Not even a little bit.
But if you tell them to find the vector of a room to avoid a fictional flesh-eating acid spray, suddenly they care.
It's totally different.
It penetrates their own system of meanings because the stakes, even fictional ones, are thrilling.
And perhaps the most crucial category mentioned in the paper is sentimiento de capacidad, building a feeling of capacity or competence.
I imagine that's huge for math.
It is. Traditional math classes often make struggling students feel inadequate. They get a problem wrong, they feel stupid, they shut down.
We've all been there.
But when a student feels they are capable of deciphering a complex 9-digit coordinate system to survive a death maze, their confidence skyrockets.
They aren't just passing a test, they are conquering a puzzle.
If we connect this to the bigger picture, the ultimate pedagogical goals here are psychological, not just mathematical.
How so?
The paper discusses differentiation psychologica, treating the student as a unique individual capable of independent thought, even arriving at conclusions differently from the teacher.
Oh, I love that.
It also highlights comportamiento de compartir, fostering a behavior of sharing, cooperation, and mutual help, much like the characters trying to survive together in the film.
But as a teacher, how do you actually grade this? You can't just hand out a blank piece of paper and say, figure out the room, don't die.
Right, there needs to be structure.
What were the actual assignments the teacher handed out to these kids?
Well, the paper outlines a specific set of activities, each with a unique evocative name to keep the narrative alive.
Oh, that's smart.
The first is called peligroso, which translates to dangerous.
I love that. It sounds like an arcade game level, not a worksheet.
Exactly. In Peligroso, students practice trial and error. They are tasked with finding the largest and smallest 3-digit prime numbers and factoring numbers to find the traps.
Okay, so heavy math, but disguised.
And they even have to correct translation errors from the movie. Apparently, the Spanish-dubbed version of the film had Kazan doing some incorrect calculations, so the students have to find and fix the movie's mistakes.
That is a phenomenal way to build that feeling of capacity. The teenagers are literally sitting there correcting the math of the supposed genius character on screen.
It really is brilliant.
You can imagine how empowering that feels for a 16-year-old. Then there's the second activity, called pharaonico, or pharaonic, referring to something massive and monumental.
Right. Here, they have to deduce that 26 cube edge lengths we talked about earlier. They have to calculate the total volume of the giant cube and then compare it to real-world objects.
To give them a sense of scale.
Exactly. The goal is to force them to truly visualize the massive scale of the structure in physical space.
It transitions them from pure abstract algebra back to physical geometry. The third activity is named E per se move, a slight misspelling of Galileo's famous phrase. And yet it moves.
Right. And this one requires drawing 3D Cartesian projections. The students have to mathematically prove which cubes never move throughout the entire structure.
Wait, some don't move.
Yeah, and they have to figure out which ones only move in a straight line and which ones move across a 2D plane.
Oh,
They're generalizing the algebraic rules to map the physical behavior of the space.
Here's where it gets really interesting. The fourth activity is called claustrophobico. The teacher gives them a 2D abstraction of the cube, like a flat labyrinth where the squares are determined by 2-digit numbers instead of 3.
It's essentially a simplified, flattened model. If they truly understand the 3D movement mechanisms, they should be able to explain how the 2D version works.
It's like playing a lethal, flat game of chess where the board itself is constantly rearranging while you're standing on it.
That's a great way to put it.
The brain is forced to stop relying on rote memorization of the 3D steps and start generalizing the formulas. For example, the activity asks them to mathematically prove why, in this 2D system, the coordinates must always result in even numbers.
They can't just guess, they have to symbolize the results algebraically.
Finally, the project pushes beyond the movie entirely. Once they understand the mechanics of a simple cube, the teacher introduces advanced space-filling polyhedrons.
And this is a huge step up.
Why these specific shapes, though? The paper mentions the students working with things called the dodecahedro rhombico, or rhombic dodecahedron, and the octahedro truncado, the truncated octahedron. Why throw these incredibly complex, multi-sided shapes at high schoolers who just learned how a cube works?
Well, think about the concept of space-filling shapes, or tessellation. A standard cube is easy to stack. You put boxes next to boxes, and there are no empty spaces.
Right.
But if you try to stack spheres, you leave massive gaps of empty space between them. The teacher asks the students what other complex geometric shapes can perfectly fill a 3D space without leaving a single gap.
Oh, wow.
It forces their spatial visualization skills to evolve beyond comfortable 90-degree angles. They have to calculate the faces, edges, and vertices of these bizarre shapes and figure out how they lock together perfectly in three-dimensional space.
So we have this incredibly rigorous multi-step curriculum that takes kids from basic addition all the way to complex space-filling polyhedrons. But educational theory is just theory until it hits reality.
Exactly.
What actually happened when Elena Tadeo tested this on real teenagers?
The paper gives us the results from 2 different locations, and the contrast is highly illuminating.
Okay, let's hear it.
First, in the 1999 to 2000 school year, it was tested at the IES Rockchabas in Dunya.
In Dinia, the students worked in groups of 5 to 6. They did the math. But the teacher also had them physically build cardboard models of the shapes from die-cut pieces, which led to class presentations and debates.
The intention was good, give them a physical object to hold, but the physical models actually turned out to be a massive stumbling block.
Really? Why?
The paper notes that the hardest part for the students in Denia was the tedious, repetitive nature of building the cardboard models. The manual labor of cutting, folding, and gluing distracted them from the mathematical theory. It bogged them down in busy work.
It's ironic that a physical model, which is usually supposed to help kids learn better by making it tactile, actually hindered their understanding because it just became an arts and crafts chore.
Yeah, exactly.
So how did they fix it?
A couple of years later, in the 2001 to 2002 school year, they refined the project at a different school, the IES Ramon Muntaner in Girivella.
In Girivella, they skipped the cardboard models entirely. No scissors, no glue. They just focused purely on the mental models, the logic, the math, and the activities, and then wrote a final memory or report on their findings.
And the results in Girivella were a massive pedagogical success. And it led to my absolute favorite detail in the entire paper.
What is it?
Let's remember who we are dealing with here. Unmotivated teenagers who typically avoid math at all costs. The teacher observed that when one group of students successfully found the answer to a puzzle, the rumor would spread around the classroom.
In a normal math class, if someone finds the answer, everyone else just copies it to get the worksheet done.
Not here. Instead of copying the answer, the other students actively demanded to understand why.
Wow.
The thrill of the challenge was so strong that some groups actively refused to hear the answer from their peers. They literally put their hands over their ears to avoid spoilers for a math equation.
That is amazing.
They wanted the satisfaction of solving it themselves.
That is the absolute holy grail of teaching. Think about the psychological transformation there. You have kids who started out staring blankly at a chalkboard, and now they are treating algebraic equations like the ending of a thriller movie that they don't want ruined.
Exactly. The criteria of sharing and independent psychological differentiation that Feuerstein talked about were perfectly realized.
Really were.
The students didn't just want the passing grade, they wanted the feeling of competence. They moved away from trying to memorize logic handed down from an authority figure and instead used their own spatial intuition.
They used trial and error.
Yeah.
They formulated hypotheses, and they moved logically from the known to the unknown. They learned to verbalize their results in an original and autonomous way, completely owning the knowledge.
It's just a fantastic outcome.
So what does this all mean? For you, the listener, you're probably not going to be trapped in a lethal shifting 3D cube anytime soon.
Hopefully not.
But the true value of this deep dive isn't about learning how to escape a fictional death trap. It is about the profound realization of how reframing a problem fundamentally changes our brain's willingness to engage with it.
Yes.
By adding stakes, a compelling narrative, and a shared goal, this teacher took highly abstract, dry data, 3D Cartesian vectors, and polyhedrons, and made teenagers literally fight for the right to solve it.
This raises an important question about how we approach learning and problem solving at any age. Teaching, or even self-education, isn't about feeding facts into a resistant brain.
Not at all.
It is about creating an environment, a context where the brain naturally wants to hunt for the answer. When the narrative is right, the human mind is capable of untangling incredibly complex systems.
Which leaves me with a final thought I can't quite shake. We all have things in our adult lives that feel exactly like that dry math on the chalkboard.
Oh, absolutely.
Balancing our finances, organizing a complex work project, even figuring out a new diet or physical health routine. It feels disconnected, tedious, and boring.
It's the adult version of the word problem.
Exactly. But if a terrifying fictional narrative can trick high schoolers into solving advanced 3D Cartesian vectors for fun, what other boring aspects of our daily reality could we instantly master if we just map them onto the right extreme, high-stakes mental narrative? Maybe paying your taxes or organizing your calendar isn't just a chore. Maybe it's deciphering the coordinates before the room shifts.